Hello everyone. In this video we will present the Archimedean property, which is named after the ancient Greek mathematician Archimedes. Before that, let's discuss some applications of the completeness property. Let S be a non-empty subset of R that is bounded above, and let it be any real number. Define the set A plus S to be the set of all A plus S where S is in the set S. We will prove that the supremum of A plus S is equal to A plus the supremum of S. Let U be the supremum of S. Then X is less than or equal to U for all X in S, so that A plus X is less than or equal to A plus U. Thus A plus U is an upper bound for the set A plus S. We have the supremum of A plus S is less than or equal to A plus U as the supremum of A plus S is the least upper bound. Now if V is any upper bound of the set A plus S, then A plus X is less than or equal to V for all X in S. So X is less than or equal to V minus A for all X in S, so that V minus A is an upper bound of S. Therefore, U equals the supremum S which is less than or equal to V minus A. Then A plus U is less than or equal to V. Since V is any upper bound of A plus S, we can replace V by the supremum of A plus S to get A plus U is less than or equal to the supremum of A plus S. Since the supremum of A plus S is less than or equal to A plus U and A plus U is less than or equal to the supremum of A plus S, we have the supremum of A plus S is equal to A plus U, which is equal to A plus the supremum of S. Suppose that A and B are non-empty subsets of R such that A is less than or equal to B for all A in A and all B in B. We will prove that the supremum of A is less than or equal to the infimum of B. Given B and B, we have A is less than or equal to B for all A in A. So B is an upper bound of A. So the supremum of A is less than or equal to B since the supremum of A is the least upper bound. Since the supremum of A is less than B is true for all B in B, the supremum of A is a lower bound for the set B. So the supremum of A is less than or equal to the infimum of B as the infimum of B is the greatest lower bound. The idea of upper bound and lower bound is applied to functions by considering the range of a function. Given a function f from D to R, f is said to be bounded above if the range f, D, is bounded above in R, that is there exists a real number B such that f of x is less than or equal to B for all x in D. Similarly, f is bounded below if f, D, is bounded below. We say that f is bounded if it is both bounded above and below. This is equivalent to there exists a real number B such that the absolute value of f of x is less than or equal to B for all x in D. Now let's proceed to the Archimedean property. If x is a real number, then there exists a natural number n such that x is strictly less than n. Suppose the statement is false. Then there exists a real number x such that for all natural numbers n, we have x is greater than or equal to n. So the set of natural numbers has an upper bound. By the completeness property, the non-empty set n has a supremum U in R. By the lemma in the previous video, there exists a natural number m such that U minus 1 is less than m. So U is less than m plus 1. From my earlier video on mathematical induction, we proved that n is inductive. So m plus 1 is a natural number. Then U is not an upper bound since it is less than a natural number. Contradiction arises. Let's prove some corollaries of the property. Corollary 1, if t is greater than 0, then there exists a natural number n such that 1 over n is less than t. Let t be positive. Then 1 over t is a real number. By the Archimedean property, there exists a natural number n such that 1 over t is less than n, which implies that 1 over n is less than t. Corollary 2, if S is the set of all 1 over n where n is a natural number, then the infimum of S is 0. Since S is non-empty and bounded below by 0, it has an infimum W. As 0 is a lower bound and W is the greatest lower bound, we have W is greater than or equal to 0. For any epsilon greater than 0, there exists a natural number n such that 1 over n is less than epsilon by corollary 1. So 0 is less than or equal to W, which is less than or equal to 1 over n, and 1 over n is less than epsilon. Since the choice of epsilon is arbitrary, by the lemma of my earlier video on absolute value, we conclude that W is equal to 0. Corollary 3, if y is greater than 0, then there exists a natural number n such that n minus 1 is less than or equal to y, and y is less than n. Define E to be the set of all natural numbers strictly greater than y. Then E is a non-empty subset of n by the Archimedean property. By the well-ordering principle, E has a least element n. Then n minus 1 does not belong to E. So n minus 1 is less than or equal to y, and y is strictly less than n. These three corollaries are sometimes referred to as the Archimedean property of R. This is the end of the video. If you find my videos interesting, please consider subscribing my channel, liking my videos, and commenting down below. Thank you. See you in the next video.